In the previous video, we have already seen how the circuit on the screen works. This is basically a differential amplifier, and the output of this circuit would be VO equal to R2 over R1 V1 minus V2. But we also saw that one of the problems with the differential amplifier is that the input resistance of the amplifier at both V1 and at V2 is not very high, which means that it may load anything that we connect at the inputs here. So one solution to that would be to connect voltage buffers at both V1 and V2, right? So we looked at that as well in a previous video. So let me just draw that. So one solution to this would be to draw a voltage, put a voltage buffer here and connect the source V1 here. And similarly, what we can do is we can connect a voltage buffer here and we can say, well, I'm going to put this voltage buffer and connect V2 here. So what happens is V1 and V2 now see an infinite impedance here. So no current flows through V1 from V1 and V2, and therefore they are not loaded. And if the op amp is able to supply enough current to the differential amplifier, the circuit works without any distortion, without distorting V1 and V2. But what we'll do, but there's another issue here. And that issue is related to the fact that for the output to be a difference of V1 and V2, this resistance R1, the value of this resistance and this resistance has to be exactly the same. And the value of R2s should be exactly the same. Let's look at that issue in the next slide. Now, in most differential amplifiers, we make sure that both this R1 is equal to this R1 and the value of this resistance is equal to this resistance by manufacturing processes. Okay, and when you build it, you're sure that this R2 is equal to this R2. But let's say by some means this R2 is not the same and there is a small difference. Okay, and I'm writing X as the fractional change of R2. Now, what is going to be the output of this circuit? So we can look at the output because of V2 alone. And if you look at the output because of V2 alone, that is the output when V1 equal to 0, we get that the output is going to be minus V2 R2 over R1 1 plus X. Okay, it's fairly straightforward. And similarly, if we look at V output when V2 equal to 0, what we get is, so we get V1 times R2 over R1 plus R2 times 1 plus R2 1 plus X over R1. You can, we've already done the steps for calculating both these terms in a previous video, and that's why I'm just writing the results here. Now you can reduce the equation here further, and what you would get, you should be able to get a term like this. It's just basically algebraic manipulation here. And what I get is something like that, this. So you get R2 over R1, 1 plus R2 over R1 X by 1 plus R2 over R1. So what is the total V output? So V output is going to be the addition of this term here and this term here. And what do they give you? Let's also, just for convenience, write R2 over R1 as gain G. So what we get is, we get G times V1 minus V2 minus V2 GX plus V1 GX by 1 plus G. So you can see that what's happening is that we are not just getting a difference of the two signals, but we are also getting this extra terms here, and which kind of distorts our output. We are not just getting an amplified version of the difference between V1 and V2, but we are getting some extra terms here, which we would not like. Similarly, you can actually see what happens when R1 changes by a certain factor. So what happens is it kind of the output no longer just remains a difference of V1 and V2, an amplified version of V1 minus V2, but it's got these distorting terms. Now, it would be nice then to do something like this. Could we make a circuit where you have this R1 and this R2 actually fixed by a factory made process so that they are exactly equal? And then what we do is we have one resistor that we can change to change this gain. Let's look at a circuit like that in the next video.